as a person who has been speaking in public for quite a while, I'm aware of the fact that people don't necessarily read abstracts or titles, or don't read them closely, particularly if there's only one track. It's like, well, you're going to be in this room anyway. So this talk is called Evident Code at Scale, and I want to talk about code and scale quickly and then move on to the word evident. I'm not talking about web scale here or data scale. Data scale is kind of orthogonal to the interest that I have here. Right? I can make a one-line program that can do 1 trillion things, right? That can process a lot of data. So I'm not talking about that kind of scale. I'm talking about what it's like when projects scale, when they change course, right? So when a project is going in one direction and it changes course and picks up new things over time. And I think this is particularly important at this point in Clojure's life cycle because we're past the initial wave of adoption and we're getting people who are coming behind that wave and they're asking questions like, wow, this looks really great, but what's it going to be like when my code base is doing 10 times as much stuff? Accomplishing 10 times as much value. How is it going to be to manage that? And notice that I was careful not to say that the code base was 10 times bigger. I only said that the code base was accomplishing 10 times as much stuff, because that's really what we care about, right? We're afraid, we think that the size of a project is a proxy for problems, right? The length of the code is scary, but it's really about getting things done. And we're going to talk about what it means for code to be evident. I'm going to follow Dick Gabriel's lead from yesterday, and you don't have to read any part of the slide except the colored part. You can ignore the dark text. So evident is perceptible, clear, obvious, apparent. And I'm going to be giving examples from the 2 projects that I've had the chance to work on over the last 3 years, which is Clojure itself and Datomic. I want to start with declarative programming because the word declarative and problems with the word declarative really led to Rich's desire to reach back into the dictionary and try to stuff something into a new word or an old word again into the word evident. And declarative programming, as we all know, is incredibly awesome. And in particular, it is about saying what the program should accomplish rather than how the program is going to go about accomplishing it. And we're going to look at this through a small example first, which is rock, paper, scissors, lizard, Spock. Those of you who are in the training class, this is taken straight from the code example from the training class. And so here's a nice declarative statement about the rock, paper, scissors, lizard, Spock domain. And like any good agile developer, I actually simplified the problem down to just rock, paper, scissors. I'll get that one right, and then I'll figure out, we'll go enterprise and we'll add lizard and Spock later. So this is great, right? Anybody can read this, right? Paper dominates rock. I hope I got these right. I was typing this kind of late at night. Rock dominates scissors. Scissors dominates paper. That's nice and declarative. It's not enough to make the program go. So you end up doing something. And here we have a winner function that is a referentially transparent pure function that uses that dominates map to say, given 2 plays in rock, paper, scissors, which one is the winner? Now, one of the things that's interesting about this is it already sort of gets to the idea that you could be declarative at one level and not at another. Right? You could have something that's beautiful and declarative, and underneath it, that thing could be functional, right? Not a logic program, but a functional program, or even an imperative program. Would this winner function be better or worse if I went to traditional mutable Java approaches and made a stateful object that represented that guy and had him change states? That'd be better or worse? Worse for some value. What if I made a logic program out of that? If I took that and did it in core logic, what would the core logic version of this be able to do that this version can't? It would be web scale. No. What would the logic program be able to do that the functional program couldn't? Right? The logic program could run in a bunch of different directions. Right? So even though this is purely functional, there's still an order to it. Right? There are inputs, and then you get to an output. If I was the logic programmer, you could run it forward or you could run it backwards. I could say, here's an outcome in a play. What was the other play? Right? Or here's an outcome, generate all the plays, right? So you can run it in a bunch of different directions, which is why logic programming is the bomb, and we should all be abandoning functional programming and heading straight as fast as possible to logic programming. So everything should be declarative. Everybody should just reach out and give your inner state monad a hug and just forget about ever doing anything that's stateful, those reference types in Clojure, stuff like that. You don't need that. Well, there are clearly reasons not to be declarative. The obvious one, and I think Clojure does this great, is you can have a functional, not in the functional programming sense, but a functional requirement to have identity. Right? If we said that the rock, paper, scissors is an online game and I can watch you as you play and see what you're doing, we've now created a requirement for identity in the system. Likewise, you could have non-functional requirements that might push you off of using a logic programming approach. Maybe the logic programming approach, the search that's used by the logic engine doesn't prune your particular problem very well, and so the performance isn't there. So you'd like to be using logic, but you can't. You could also have a constraint. I suspect that the most likely constraint that you might have would be, my team doesn't know how to write logic programs yet. But that's a legitimate constraint, right? We better not build everything out of logic programs because we don't have that skill set mastered as an industry. The point here is that declarative is not a perfect word for goodness. Right? We can't slide from declarative to that's the right answer, which is phase one of motivating the use of the word evident instead. So what would it mean to write programs that were evident? A key idea, I think, in evident code is making good use of abstractions. And I have some fairly concrete advice here. I should say now, this talk is going to have a lot of code. Right? It's not going to be one of those fluffy, rich, hickey idea talks. There's going to be a ton of code, and there's going to be really specific advice. So in Clojure, we have protocols as our primary way of talking about abstraction. We have other ways as well. And it turns out that there is an ideal number of methods in an abstraction that you should be aiming for. Which is 0. We abstract too much. We make up abstractions where abstractions do not exist. When we have abstractions, they are often fantastically big and conflated. I'm going to show 2 examples of ugliness that comes from this that both come from awesome libraries. So I don't want this to be taken as criticism of the libraries in question. The first one is from Java itself. So this is the map interface in Java, and it's way too big. What's rolled together in here? If you're not sure, go and look at all the Clojure interfaces that maps implement that break this out into the different pieces that it ought to be factored into. And you have to ask yourself, why do Java interfaces end up looking like this? One piece of the problem is that people don't think carefully through and carve out really small abstractions. But I suspect that a real cause of the problem is that people don't want to have to write casts. Right? So they have these 3 things that they commonly use together. And just because of the way the language works, because they would have to write casts back and forth all the time, they end up making things like this so they can treat this thing as a cohesive whole. The other problem is that in all too many programming environments, we end up using the same mechanism for abstraction and for concretion. Right? So we have methods and classes to represent abstractions, but then we use methods and classes to represent things as well. This is one of the request objects from the AWS API, which is a terrific, really capable API, and it's really well thought out, and yet it has these awful, ugly concretions in it. And the funny thing about it is, how many people have used the AWS API from Java? Say about 10, 15% of the room. If you use this for a while, you start to get a sneaky suspicion that the AWS API was actually written by a program. Right? They actually have, I suspect, a data description of all of this that actually they run through some transformer, which they have not published, which emits the Java program. So they don't actually live in this world. They're not forced to work with these concretions in this kind of shape. So we have a lot of problems getting abstraction right just from the get-go. And we have a lot of bad examples or misleading examples, even in really good libraries. And probably the biggest thing, especially when you're introducing people to Clojure, that you're going to run into, and I get this again and again and again, is, wow, this all seems really great, but where's encapsulation? Right? Yeah, this immutable data is really cool, but where's encapsulation? And there actually is a way to talk about that that's useful. This is not computer science. This is just dictionary definition of abstraction. The job of abstractions is to reduce the information content of something so that you can deal with it and not have to deal with the whole of the thing, just deal with the part that you care about. And if you take this notion of abstraction and you combine it with Rich's picture of the epochal time model in Clojure. So this is, if you haven't seen this picture before, that box moving across the middle is some sort of Clojure reference type over time, and pure functions, advanced reference types from one state to another, and then down at the bottom there are observers. And if you take the notion of abstraction as reducing information, it becomes clear why, if you don't make this separation, people get really confused about what encapsulation should do. If I have an abstraction around action, around function, then that's saying I have to provide less information to make this action go. That's a good deal, right? You know, I have to know 6 things to trigger this thing in the system. No, I want to know only one thing. I don't want to know a bunch of details in order to trigger something in my system. On the other hand, abstraction on the perception side is just reducing the amount of information I can get. Right? We make something smaller on the I have to do work side. That's great. That's less work I have to do. We make something smaller on the observe side. Not so good. This is not licensed to observe all kinds of things you don't need to observe and make yourself unnecessarily dependent on them. But it is, I think, an argument against an object-oriented programmer's need to go through and encapsulate everything. Right? Because all they're doing is hiding information from themselves after you break the world into action and perception. So Datomic has about 50 protocols or interfaces, and they are divided between action, things that are on the top of that slide, and perception. On the action side, there are protocols that describe the relationships between the services. So if you look at the 3 different things that Rich called out, the storage layer and the transactor and the peers, right? There are protocols or abstractions between them. There are also smaller protocols and abstractions inside the various moving parts, typical design to make those kinds of abstractions. And then there are also abstractions around perception. It's unusual in most Clojure programs to create new abstractions for perception. What abstractions do we use for that? Maps, vectors, seeks, and so on. But because Datomic is a database, it has actually a few new generic data structure types that don't actually map to any of the perception interfaces that are already in Clojure. So one example of that is entity. So this is a perception-related abstraction. Right? This is some way to let me find out information. And this lets me walk up to something that I got out of the database and say, what attributes can I see about you? And here's an action example. So this is that portion of the Datomic API that updates the database. That's all of it. That's the entire update abstraction in the entire system. Right? Just those 2 methods. So the total size of update is 2. Now remember, I told you, what's the ideal size? 0. So I apologize that the Datomic has such a bloated API that there are actually 2 methods that you need to have to make updates. We'd like to try to do better. As we go through the talk, maybe we'll find a way to do a little better than that. And so the things I would say about abstraction when you want to make code evident is that abstractions need to be fine-grained. So a small number of methods, preferably 0. Abstractions need to separate perception and action, which comes fairly naturally in Clojure because you don't write perception-related abstractions. Right? You don't sit down and write beans with getters, right? You just use maps. And when you make a def record, you don't get a new perception-related abstraction. You continue to use the abstractions that are already provided for you. So perception is generic. This is probably fairly easy to do naturally in Clojure, right? If you're just following what others are doing, you're going to get this right to a pretty good degree, although the fine-grained abstraction part is always hard. I don't think that abstraction is necessarily the most important part of evident, though. I think that actually data values, programming with data, does more to make a code base evident than abstraction can. And I'm going to show several examples of this. The first one is queries. So data log queries in Datomic are data. And we're going to go through this quickly. This overlaps, those who have watched the little 10-minute video, this overlaps with that some, but I'm going to call out some different points as we go. So a data pattern describes something you want to look up. So it's going to constrain results and bind some variables. And in this data pattern, the data patterns follow entity, attribute, value, transaction. In this case, we've left out transaction because we don't care about it. And you can put a constant in a data pattern. If you do that, it acts as a constraint. I'm only asking questions about the email attribute. You can put a variable in, and that says fill in the blanks with these. Give me back customers, give me back emails. The choice of where you put constants or variables is up to you. So here I've put a constant in entity position. So now I'm saying find entity 42's email. You can also put the variables anywhere. So here I'm saying tell me all the attributes that entity 42 has. And I'm not saying the values of those attributes. I'm saying the attributes themselves. Right? 42 has a first name. If I actually want to find out what 42's first name is, then I could put a variable in the value position as well. You take these data patterns and put them into a find clause to specify what pieces you want to get back. So the find clause is going to have one or more variables to say this is the piece that I want to get back. And then you can start to build up bigger things out of it. So here we have, I would like to find everybody in the system who has an email and has placed an order. And we're using email as our way of identifying customers. So find all the customers who have placed orders. And this is the point where I want to draw the distinction carefully between being declarative and being evident. And this is declarative and evident. But a declarative approach to this doesn't have to be evident. And you can tell that I was writing slides late there. We'll scratch that. We'll wipe that out in the video. So I could have a declarative, logic-based query language that declared what intermediate tables that I had to go through to do that join. It would still be declarative. Right? It would be go get email and go get customers. But it would have to navigate structure as well. And people would tend to say that that's still declarative, right? That would be in SQL or that would be in a logic programming language. That still is within the purview of being declarative. I could have a declarative XML language that explained how to convert everything that was coming out of the database into objects. That's still declarative, but it's not making my code more evident, right? To create that second source of truth or possibly confusion. And maybe the most interesting or subtle one is I could have an explicit connection or an explicit value in my query language, or I could have an ambient value in my query language. When you talk to a SQL database, the notion of what the database is doesn't show up in your query. Right? You're just talking to the database. And that makes sense because you're going there. Right? You're going to this place that is the database, so you don't need to say what that is. What limitation does that put on you? You have to go there. What else does it put on you? How many databases can you query against? One. It's ambient, right? You don't have a chance to say, oh, I want to query against 2 databases. So this is 3 examples of you could take this purely declarative thing and muck it up and have it be a lot less evident. Right? We could have structural navigation through a document or through a join table, or we could be converting it to objects, all declaratively, and hurting the evident nature of the code. So the query API looks like this. So now we're plugging that query in. So Q is the query function, and this query takes our query, and then in this case a single input, some value of the database. Now let's move to having more than one input. So you can add an in clause to a query that says I'm going to have more than one input. If that input's a database, it's $ prefixed. If it's a variable, It's question mark prefix. And that lets you do things like a parameterized query. So here we have a first input, which is the database, and a second input, which is the email that we want to look up. Of course, you notice that now that we have more than one input, we have to actually specify the input in the where clause. And so that gets to be verbose. Right? I'm not going to type the word database all the time. So it's idiomatic just to use the $sign. And in fact, it's idiomatic just to leave it out. Right? Because even though we don't want to be limited to querying one database, a lot of times, how many databases are we querying? One. Right? So we want to have that be as easy as possible. So you can extend these queries with predicates. So you can, I should also mention, by the way, that all of this stuff is in this really novel new programming language called the Datomic query language. It may look extremely familiar to people in this room. So I'm not going to bother to explain the syntax and where the parentheses go and, all that kind of stuff. So this predicate says the price is greater than 50, and you can add predicates into your queries like that. You can also add functions into your queries. So here we have a shipping function that says, given a zip code and a weight for a package, tell me how much it's going to cost. So functions take arguments. They have to be bound for the function to be invoked. And then they bind variables with returns. And so here we have a substantially more interesting query. This says, find me all the customer product combinations where the shipping cost dominates the product cost. Right? We're worried that our customers are unhappy because they try to buy something and the shipping cost is actually more than the cost of the thing. And so in order to figure that out, you actually have to implicitly join across the customer and where they are and the price of what they're ordering. And then you have to call out to this shipping estimate function. And that shipping estimate function can be just any old function. In fact, it could be a web service call inside your query. Now I'm going to show you one more query. And I'm not going to explain it in detail. I'm going to go quickly. So this query says, find all the people in our system who have recorded interests. So we have something in the system that lets people say, I'm interested in football or whatever, as entities, and make datums. So this is a query of the database that manufactures datums. What is this? What is this query? It's an ETL job. All in a query. Right? It's a pure function. It's a logic program that takes data from one data source and produces the input that you pour into another database to put datums in that database. So, hereafter, I know you guys like to call it thread last, but this guy is now called the ETL macro. Schema is data. So here is a description of a single attribute. This is from a parts catalog. So the attribute is called part name. It's of type string. A part can have only one name, so it's cardinality 1. It's full text true because parts have these long, interesting names, and we want to find the, purple screwdrivers or whatever. And this actually came up on the Datomic mailing list this week. Somebody said, that's a mouthful. Why don't we do this instead? So we're going to have this thing called create EAV, and it's going to do all the work that other guy did, but I'm not going to have to type as much. Well, what's different between these two things? Quite a lot, right? With that map describing the schema, I have this incredibly large API for manipulating schema definitions. What is it? The map API. It's not just Clojure, right? You could do it from Java, right? You could call all the map API functions in Java. I can make those schemas from any language. And this is really important. I can read schema without evaluating it. If we go to a function at the bottom that makes schema, then you have to call that function. Which, by the way, what does that do to the API for everybody who's not coming from Clojure? Right? You can see how this cascades, right? If I'm going to do this, then we got to expose create AAV in some way that people can call it from Scala and Groovy and JRuby and whatever. The name versus positional argument also has to do with the data being able to be self-describing. And of course, with maps, I can extend it easily. If I wanted to say an additional fact, and remember that Datomic is an open system, right? You can add any kind of datum to any kind of entity. If I wanted to add some new fact to the schema, like this guy, let's add units of measure, right? So whenever we have a numeric type, we're just going to have a convention that we also record what the unit of measure is for that numeric type. What do I have to do if my schema is made out of maps? We have an API for that, right? A SOCH. Or I can just type the map literal. And of course, I can build these things from programs. So we've seen that query is data, and now we've seen that schema is data. Here's a more subtle one. Navigation is data. So let's go back and think about that entity interface again. So I'm holding on to an entity, and I can say, let's say it's a person. I can say, tell me all the attributes that we know about you. And if one of those attributes is an entity, I can jump right down there and say, okay, now tell me all the attributes about you. So I'm really close to being able to navigate the entire database just by calling those two methods from entity. What's the fly in the ointment? Well, all those relationships are directional, right? So I've said that a person has an address. What if I want to go the other way? Well, the API solution is pretty straightforward, and we have to come up with a better name than reverse get. But we're going to add a method to the entity API that says, well, if I'm navigating from an entity to a value, I call this, and if I'm navigating to what entity has me as a value, right? If I'm going the other way, then we'll call reverse get. This is a disaster because it takes away the data nature of navigation. When the navigation is just data, I can navigate all the way around the database by saying things like this. Tell me what town Jack lives in. Now, what if I want to know who else lives in Jack's town? Right? The underscore, which is still data, says navigate that relationship in the reverse direction. So this says go from Jack to his town and then give me all the people in Jack's town. And navigation is data, which means that, and this is the slide I'm happiest about, so I want you to burst into wild applause. The number of methods in Datomic's graph navigation API is 0. That's win. Right there. Now I'm going to talk about some other stuff. Enough about evident code. Evident code is not really enough to understand a substantial application. And so there's a ton of other stuff that we used while building Datomic. One thing that we used that was really refreshing is specifications. Right? So some major components of the system actually have prose specifications before they have anything else. And obviously that's a careful upfront design kind of thing. So I know it's out of fashion, but it's still kind of useful, it turns out. We have doc strings. We make heavy use of pictures. We draw lots of pictures. I would suspect we have several hundred graphal things right now. And we do a ton of outlines. Right? The primary thing when I sit down, formerly I would have written give and win then. That's, sit down and start typing. Now I just start writing those little asterisks and making outlines and posing questions and saying, here are the constraints that we have to trade off and try to get everything sort of laid out. And then we probably should test this, given that it's a database. Maybe a little. So I heard it said that tests were executable documentation, which is really good news because my abstract didn't say anything about testing, and I want to talk about testing some. But because of this, it's now part of being evident to have a test suite, so I get to actually now make a right-angle turn in this talk and talk about testing for about 10 minutes. So what is a test? There's a bunch of different pieces that go into a test. You have inputs, right? There's got to be something going in. Some sort of driver that does the actually execution. Output capture. And then you probably have validation. I've separated out validation because if I had a test that just ran the program and didn't actually look at the outputs, it's still doing some minimal validation. What's it doing? Make sure it didn't crash and make sure it doesn't hang, right? So there's a little bit of validation in there. A test could also usefully communicate things about the system. Certainly we want that. I don't know how much we want that. I'm not sure how we will trade it off with other things, but we would like our tests to communicate about how our systems work. But you wouldn't say I didn't have a test suite because it was hard to read and didn't communicate. Right? You wouldn't invalidate its status as a test suite. You would just say it's an irritating test suite. They would still be tests. Likewise, I would like my test suite to have record of what has happened in the past. So for regression, for example, I'd like to know what happened when I ran the test suite before. So when I run the test suite again, I can get some assurance that things haven't changed, for example. So this is an example from Clojure's test suite, and it's typical unit testing style. And it complects all of the different key elements of testing inside of individual functions. So we're actually testing that Clojure can add numbers here. And so the driver is the R macro in Clojure.test, and the inputs are hand curated, right? Somebody sat down and thought up those inputs. I'm pretty sure that's comprehensive. That covers all the numbers that you might want to add in Clojure. And then there are these outputs, and those are hand curated as well. So rather than do that, one thing that we like to do, and in fact it's great that Datomic is out now, I wrote test generative as part of testing Datomic. So when I shipped that last year, it was something that had been built internally to help us with testing. And I'm going to show one quick example of generative testing. And I'm going to use the same example that Aaron and I use in the book, which is this game which is called Codebreaker, or under the trademarked name Mastermind. Now that I've said the trademark name, you should all go and buy the real Mastermind from the real Mastermind people and tell them that I sent you, so that they'll be happy at this reference to their trademark stuff. And so the idea, how many people have played Mastermind? The real trademarked one? Okay. So the idea in this game is that you're guessing these colored pegs, and you get 2 bits of information after each guess. How many colors are in the right spot, which is the red pegs on this particular little game, and how many colors are right but not in the right spot. How many pegs are a matching color. And so to test something like this generatively, you want to have a function that generates inputs. So this is for a 4-slot version of Mastermind. So this is a random secret. Then you have the function you want to test. So this is the scoring function, and we don't have to worry about the details of it. I'll just observe that the scoring function returns a map of the 2 things that you need to draw the UI, the number of exact matches and the number of unordered matches. And then you have some validation functions about invariance. So it turns out that scoring in Mastermind is symmetric. If you took my guess and said that was the secret and flipped it around, right? Is it symmetric? It's actually useful to think through these things when you're right. It is symmetric. Also, it's certainly the case that scoring is bounded by the number of pegs. Right? If I'm only playing a 4-peg game and a score comes back that adds up to 5 pegs, we know something is wrong. And the first thing that's important about this is that you've separated input generation and the function you want to test and the validation. The second thing is that when you approach validation in this way, you end up not being in the same mindset you were when you wrote the code. And actually, preferably, it would be just somebody else writing it, given the spec. Right? This whole notion of you write the test and you write the code is a perfect recipe for making the same mistake twice in a row in a short time period, and then having something that makes it look like everything's okay. Right? It's not a good deal. I'm not saying quit doing it. It's better than not doing anything, but it's not as assuring as one might like it to be. And then in test generative, these things are all connected together by a driver macro called defspec. And so inside of a defspec, you have a thing that looks like an argument list, which actually describes how to generate arguments. And then you have the function under test and the validations that you want to apply. So Aaron gave a talk about this. I guess some people saw it. I saw a couple of tweets. I think this style is useful. I do not make any pretension that test.generative is thorough or complete or even up to snuff to similar libraries and other functional languages where people have been doing this for a long time. So if people want to jump on it and contribute a bunch of improvements, that would be most welcome. The other thing that I would point out, though, is that in the Mastermind case, you could actually just do all of them. Right? In Clojure, adding numbers, I didn't really have the option of saying we're going to just do every possible scenario. But in 4-slot Mastermind, you could actually print out a table that has every possible scenario. And this is pretty cool because you print out this table and then you hand it to somebody and say, jump around at random and spot check 50 of them and tell me if they're right. And then we will save a record of that test and start running it as regression without having to hand write any validation code. And you might not choose to do that. You might say, you know what, I want to be more careful than that. I want to read through all of it. Or I want to hand write some validation code. But the fact that we have separated input, execution, and validation lets you make independent choices. Lets you say, I want to do this part and not that part. Test inputs and outputs are made of data. And so there's a lot you can do with test inputs and outputs And this is not going to be up to snuff with the fancy visualizations that we've seen in some of the other talks. So I'm a textual guy. I'll just put that out there before I show you these lovely ASCII art graphics. So here's an example of a test suite for the Brian's brain simulation. So here we have little pictures in ASCII art of different states of the game, and then a keyword that says what state are we supposed to go to next. And so once you have learned the rules of the game, it's a lot faster to look at these little pictures and say, is that right, than to have some 9-entry data structure that says, what is the current relevant state of other spots on the board next to me. So this is one example of taking test data and making it more visual. Another example is to have your tests write documentation. So this is a table of the different binding forms that are it's actually elided. This table would be a lot longer and have more columns, but I chopped it down so it would fit and be semi-readable on the slide. But this is a table of the different binding forms that are possible in Datomic's query and how they work. The really cool thing, though, is if you lived in a world where you were careful to think about time as a reified thing, then stateful interactions are themselves data. Right? Because once you add the time element, right, you just have, right, this is the point about datums having that transaction where you can get back to time. And so you can start to have tests that are a table that shows a series of events over time. So this is a example usage pattern of queuing abstraction, showing that as I put things into the queue and offer things from the queue and pull the queue, what happens. And so each line represents a point in time of the test. Of course, where it gets really exciting is when you start to test interleavings. So this is a test of how Datomic's peer will automatically reconnect when the transactor dies and fails over. So your transactor dies, and you're a cheapskate, so you weren't running another one. So 5 minutes later, Amazon gives you another one, and then the peers reconnect. Or your transactor dies, and you're on a big budget, and you already had another guy sitting there waiting, so in a few seconds, you roll over to that guy. But the peer has to go through this thing that includes retries and backups and attempts to clean up the Java resources of the connection and all that kind of stuff. And so this little output here, and this is, again, heavily elided, is from a simulation run where I'm simulating a series of 50 straight transactor failovers. Right? So I'm making it seem as if the transactor dies, and then these letters are just letter codes that I made up of different events that happen. And then you can look at this. I, the human expert who was working on this, can look at these letters and say, is that interleaving possible? Right? Could we do the cleanup action and then fall asleep? And then is that possible or not? Now, obviously, in a perfect world, what would I do with these interleavings if I wanted a really good test here? I'd write a logic program of some kind that looked at them and actually could just tell me, are these interleavings possible? I don't have to do that at first, though, again, because I have separated out running the test, capturing the results, reviewing the results by viewing them, and validation. I can choose how far I want to go down the road. So if this is a particular pain point in the system and I want to go further down the road, then I can write a program that evaluates this. Now, I'm not going to have a program that reads those letters. Right? Behind those letters, that's a convenient print form for me to read. What's behind those letters? From a data structure perspective. This is Clojure. What's back there? Just lists and vectors and maps, right? So if I was actually going to programmatically assert correctness on these order of things, then I would be actually processing plain old data structures. I also want to be able to simulate failure. So here's a test that says, what happens when DynamoDB doesn't work? And in my test, I'm assuming that DynamoDB has a little more than 1 9 of reliability. Not very much. Hopefully, Dynamo is going to have several more 9s than that. But notice that my storage fail rate there is 1 in 20. Right? One time in 20 that I try to use storage, it's going to fail. Now, there is not a one-to-one correspondence between storage failures and writing a block. So this is simulating a failure, writing the log. What are the data structures in Datomic when they're put on disk? What is always the answer for what is a data structure in Clojure? Underlying data structure. What are they? Trees. Immutable trees, right? So many times doing something is going to write one thing, but every once in a while it's going to write more than one thing, right? It's going to write other pieces of the data structure as you have to write intervening nodes. And so there's not necessarily a trivial mapping between a failure at the write level and then what happens up here. So the question then is, well, there's a couple of questions. I wanted to try to write 100 log blocks. I succeeded in writing 100 log blocks, even with a failure rate of 1 in 20, because there's a built-in retry strategy. And there were 9 retries. The question is, how do I know there were 9 retries? What evidence would I have for that? This is a place where I think people often go in the wrong direction, right? Because 5 years ago, what I would have reached for here is mocking and stubbing, right? I would have created this new special world that had nothing to do with my production environment, and tried to sort of play with that and figure out if this works. Well, what I want to do here is look at side effects that would happen in the real environment and try to make decisions based on those things. What would be a visible side effect of a retry? Well, let me back up. If retry has no side effects, then I don't ever need to bother testing it. Right? It must have some side effect. Right? You can always think through this. Now, sometimes it's going to be computationally inconvenient or impossible to do this. I'm not saying you can get away with never mocking and stubbing, but you can get away with it a lot more often than you would think. What evidence am I going to have that there's going to be a retry? What's that? Time. Time is one piece of evidence. What else? There may or may not be network activity, but that's a good one. This is below that, so we won't see it up at that level. That's a good guess. With apologies to Bradford, one of the other things we're going to have is logs. Right? And by the way, when we have the official Mark Granigan seal of approval, logs are maps going. But we do write logs, so we can look at things that happen. So logs, there are also metrics. So AWS has this great CloudWatch metric. So you could have a CloudWatch metric that said, ouch, I tried to write to Dynamo and didn't go well. And in fact, Dynamo has its own metrics, so you probably have already triggered a metric down at the Dynamo level in addition to the metric at your level. So there are all kinds of ways that we could get this number of retries without mocking or stubbing anything. And you can take your choice. In this case, I actually got it from the log, but there are other ways to do it. One of the things that I hope comes out of all these examples that I've just shown is that tests are programs. That sounds kind of trite. That's because I'm the master of trite. But tests are programs. And in particular, every test can be a different kind of program. Right? The unifying testing framework that we use testing Datomic is a program launcher. And you can fail the build if somebody throws an exception. Right? Because the individual programs are all very different. In particular, a lot of the programs go through this little guy. So I suspect, like many people, that when I'm testing something initially, I test it at the REPL, or I write a little script. If I write a little script and it has a little bit of validation or some exception that it would throw if something's wrong, I can throw it in a directory in Datomic, and it will run it in this incredibly brilliant custom REPL, right? That just sits there and runs it as if I had typed it in. It just prints out, then the user did this, and then he saw this, and then he did. So it's like a way to go back and reproduce an interactive session that you did at the REPL. And this is a very poor man's thing to do, right, compared to some other things one might do. But a key element to having tests is being able to have a gradation from things that are really easy to do up to things that are a lot more powerful. And so it's very easy to just take a REPL interaction and say, I'm going to add that to the test suite. Now, on the other end, this is on the super lightweight poor man's end. On the other end, we have the SIM. And the SIM is the big monster. And so the idea behind the SIM is that there is a database called the SIM database. And the SIM database has a bunch of actors, so people or processes who are interacting with the system. And it has a bunch of actions that they're going to take, described as data, and time-stamped. And then you take all of that, and you run it with a runner. The runner fires up a bunch of Elastic Beanstalk instances, and then looks at the SIM data and says, well, at time t, actor number 7 tries to do this query. And at time t plus 5, actor number 8 issues this transaction, and so forth. And so what this gives you is simulated real use of the system. And you can generate, pick your own probabilistic distributions of different kinds of activities, create different kinds of loads, and run them through the runner. And then, later, you can run validation. So a separate validator program can look at the result of running the sim. And what it's going to have access to is the sim data, which is in a database. The sim data is in this really flexible database where everything's time-stamped and there's a logic language for querying it. So it's really easy to get to. Or you could look at the thing we're testing, the orders data, so the system actually pretends to be a little catalog store. The orders data is also in one of these nice, really flexible schema databases. And the validations in this world, so there are a lot of things about this that are nice. First off, simulation is not a precious curated path, right? It allows you to have real concurrency and real separate things going on. It uses real input and output. It has a model for time. It separates your testing activities in time and space. When do I have to write the validation for the sim I ran last week? What information do I have about it? All, right? We throw all the logs into S3. We have the CloudWatch metrics. We have the database of inputs, the database of outputs. The input and output databases have timestamps. I can go back 6 years from now and write a validation and say, were we correct on March 15th? And validations can be logic programs. Right? The validators themselves can be logic programs. Now, the downside of all this is this one will take longer to set up than all those cheapy things I showed you before. So when you run out to do this, you should allow yourself at least 30 or 45 minutes. I want to wrap up by quickly reminding, I went through Datomic's code base in preparing this talk and just thought about, where did Clojure really jump out and make a difference? And in a lot of ways, this is the usual suspects, right? Immutable data, functions, Clojure's reference types, protocols. This audience knows how these things make your life a lot easier. The one thing that I want to call out is that as I was thinking through it, data really was on top. Even more than functions. Just the rigorous insistence on staying in data where possible. And you saw that throughout this talk. Queries are data. Transactions are data. Right? You saw the symptom of it in that the size of the APIs are asymptotically approaching zero. Right? There are no APIs because everything is just data. And as an industry, we've been really terrible about that. And we're starting to get better. I also think that Datomic clearly shows a lot of Clojure philosophy. There's probably some continuity in the design effort, I would argue, which causes that. And, we've talked about simplicity, power, and focus before. The thing I want to call out above all of that, though, is architecture. Or if you want to say it, upfront design. Right? Thinking through things. You can't build something substantial by taking an incremental walk from where you are. Right? To get somewhere substantial, eventually you have to leap from some local minimum to some other local minimum. And to get somewhere really substantial, you've got to get a bunch of different things in play and look at their costs and their benefits related to each other. Rich has already said these things better than I say them, right? People have watched the hammock talk and things like that. But it's super important. It's important to how Clojure and ClojureScript were designed, and it's important to how Datomic was designed as well. So, if 2011 was the year of functions, I am hoping that 2012 will be the year of data. I'd like to ask everyone to give Alex Miller a big hand. And now, because it's just ridiculous, right? I mean, you have this social mores that now you've done a bunch of applause, and now I'm done, so you have to applaud again. Don't, right? We can just be done. This has been really terrific. I hope we will be back here or in Portland or wherever in a year's time. Thanks to all the sponsors, to all the great speakers, all the great conversations, and we'll all see each other at the next big Clojure event. Thank you.